Taking a look at the VI characteristics and the curves here. Let's look at the forward bias. We can, if you look at the diagrams here, you can see what's going on with a forward bias and what's going on voltage and current wise. When a forward bias voltage is applied to the diode, there's no current. This current is called the forward current and is designated as I sub F. As the figure illustrates, you can see what happens when the forward bias voltage then is increased positively from 0 volts. The resistor is used to limit the forward current to a value that will not overheat the diode and cause damage. With 0 volts across the diode, there's no forward current. As you gradually increase the forward current and the forward bias, the forward current and the voltage across the diode gradually increase as shown. A portion of the forward bias voltage then is dropped across the limiting resistor. When the forward bias voltage is increased to a value where the voltage across the diode reaches approximately 7/10 of a volt, again the barrier voltage, the forward current begins to increase rapidly as shown. As you continue to increase the forward bias voltage, the current continues to increase very rapidly. But the voltage across the diode increases only gradually above 7/10 of a volt. And we'll see this on the curves. This small increase in the diode voltage above the barrier potential then is due to the voltage drop across the internal dynamic resistance of the semiconductive material. So what we need to do now is take a look at how do we take what we've seen here in these diagrams and apply them to a curve. So let's take a look at graphing then the curves, the VI curves. If you plot the results of the type of measurements that we just took a look at, you get what is called the VI characteristic curves for a forward bias diode. The diode forward bias, then V sub F, increases to the right along the horizontal axis, and the forward current I sub F increases upward along the vertical axis. So we can see that in the diagram. The forward current increases very little until the forward voltage across the PN junction reaches approximately 7/10 of a volt. You can see that there again with the knee. And that 7/10 at the knee then of the curve, this point the forward voltage remains at approximately 7/10 of a volt. As previously mentioned, there is a slight increase in the forward voltage above 7/10 of a volt as the current increases due to mainly the voltage drop across the dynamic resistance. Normal operation of a forward bias diode is above the knee of the curve. So once we get it above the knee, then we are in the operation for a diode. The current I sub F then typically is in milliamps as indicated on the graph. If we look at the 3 points A, B, C on the graph, then point A corresponds to a zero bias condition, nothing's happening. Point B corresponds to the figure where the forward voltage is less than the potential of 7/10 of a volt, and point C then corresponds to where the forward voltage approximately equal to the potential voltage. As the external bias voltage and forward current continue to increase above the knee, then the forward voltage will increase slightly above 7/10 of a volt. In reality, the forward voltage can be as much as 9/10 of a volt depending on the forward current. We mentioned the dynamic resistance previously. In the figure B, then, we can see an expanded view of the VI characteristic curve in part A and illustrates that dynamic resistance. Unlike a linear resistance, the resistance of the forward bias is not constant over the entire curve. Because the resistance changes as you move along the VI curve, we call this the dynamic or the AC resistance. Internal resistances of electronic devices are usually designated by the lowercase r with a prime instead of the standard capital R. The dynamic resistance of a diode then is designated as R prime sub D. Below the knee of the curve, the resistance is greatest because the current increases very little for a given change of voltage. R prime D is equal to delta VF, which is the change in the forward voltage, divided by delta IF, the change in the current forward bias. The resistance begins to decrease in the region of the knee of the curve and becomes smallest above the knee, where there is a large current change for a given change of voltage. Taking a look at then what happens with the reverse bias diode. When a reverse bias voltage is applied across a diode, there is only an extremely small reverse current I sub R through the PN junction. And we've seen this before. With 0 volts across the diode, there is no reverse condition as you gradually increase the reverse bias voltage. There is a very small reverse current and the voltage across the diode increases. When the applied voltage is increased to a value where the reverse voltage across the diode, V sub R, reaches the breakdown value, V sub BR, the reverse current begins to increase rapidly. And we can see that in the graph as the current starts to decrease, or actually increase, but in the negative direction. As you continue to increase the bias voltage, the current continues to increase very rapidly. But the voltage across the diode increases very little across the breakdown voltage. Breakdown, with exceptions, is not a normal mode of operation for most PN junction devices. And if you've looked ahead at the special purpose diodes like the Zener diode, where it is in fact designed to operate in reverse. So graphing the VI curve then, if you plot the results of the reverse bias measurements on a graph, you get the VI characteristic curve for the reverse bias diode. A typical curve is shown. The diode reverse voltage, V sub R, increases to the left along the horizontal axis, and the reverse current, I sub R, increases downward along the vertical axis. There is very little reverse current, usually a microamp or a nanoamp, that occurs until the reverse voltage across the diode reaches the approximate breakdown value, V sub BR. And we can see it marked on the graph, though not numerically, but it is in fact marked there at the knee. After this point, the reverse voltage maintains an approximate V sub BR, but IR increases very rapidly, resulting in overheating and possible damage. The breakdown voltage for a typical silicone diode can vary, but a minimum value of 50 volts is not unusual. So now what happens when we put this together, forward bias and reverse bias on the same graph? If we combine the curves for both forward bias and reverse bias, you have a complete VI characteristic curve for a diode, as shown. Notice that the forward current, I sub F scale, is in milliamps, compared to the I sub R scale in microamps. So top and bottom, the scale changes. So now we need to take a look at something called the temperature effects. You know, with most electronics, heat becomes a factor. So what happens when we take a look at temperature effects? For a forward bias diode, as the temperature is increased, the forward current increases for a given value of forward voltage. Also, for a given value of forward current, the forward voltage decreases. If we take a look at the next graph, we can see what we're talking about here. So this is shown with the VI characteristic shown in the figure. The blue curve is at room temperature, 25 degrees Celsius, and the red curve is an elevated temperature, 25 degrees Celsius, plus some change in the temperature, delta T. Notice that the barrier potential decreases as temperature increases. For a reverse bias diode, as the temperature increases, the reverse current increases. The difference in the two curves is exaggerated on the graph. For the illustration, keep in mind that the reverse current below the breakdown remains extremely small and can usually be neglected.